It's kind of crazy when you think about it. How can an AI look at a photo and just know it's you? Or write a poem that actually sounds, well, poetic? It honestly feels like magic. But like any good magic trick, there's a secret. And today, we're going to pull back that curtain using a scientific paper from all the way back in 1989. Let's dig in.
This whole thing really boils down to one massive question. Can a simple computer program, just a set of rules, actually learn to do, well, anything? Not just crunching numbers, but spotting patterns, making judgments, understanding really complex stuff. That's the dream of AI, right? And today, these programs, we call them neural networks, they're doing things that were just science fiction a little while ago. Recognizing faces, translating languages on the fly, even helping to drive a car. But the question is still there. How? How do they get so smart? Turns out, the answer isn't some newfangled discovery. It's a really foundational idea.
And to find that answer, we've got to go back in time. We're going to look at a moment right before the big AI boom, at a paper that basically laid out the secret ingredient that gives these neural networks all their power. And here it is. Approximation by superpositions of a sigmoidal function. Okay, doesn't exactly scream page-turner, does it? But this paper, by a guy named George Seibenko, gave a mathematical proof for something people had only really suspected. It showed why these networks have the theoretical ability to be so incredibly powerful. What this paper claimed was, well, it was kind of mind-blowing. Seibenko proved that even a super simple network, one with just a single layer inside, only needs one special type of component, this one secret ingredient, to be able to, in theory, learn pretty much anything. So what is this magical ingredient? Well, in the paper, it looks like this, a sigmoidal function. And let's be real, this block of math doesn't mean a whole lot to most people. It looks super complicated, super academic, but the actual idea behind it, it's shockingly simple. And this is the perfect way to think about it. All that complicated math is just describing an S-shaped curve. The best analogy is a dimmer switch for a light. It doesn't just click on or off, it slides smoothly from completely off, that's 0, to completely on, that's 1. And it can be any value in between. That's it. Seriously, that's our secret ingredient. Okay, so we've got our ingredient, this simple little dimmer switch. But how in the world do you use a bunch of dimmer switches to build an AI that can recognize a face? Well, that's where the recipe comes in. See, the big idea here is that one dimmer switch by itself isn't that useful. But what if you have thousands of them, all wired up together? By tweaking the settings on all these simple little switches and then adding their effects up, you can build basically any smooth, continuous shape or pattern you can think of. It's kind of like a painter who only has a few primary colors but can mix them to create millions of different shades. And this incredible idea that you can build almost anything out of these simple little parts, that's the real climax of the paper. It's all proven formally in what Seibenko calls Theorem 2. This is the whole ballgame. And here it is, in all its mathematical glory. This is the formal statement of what we now call the universal approximation theorem. Again, looks pretty intense, right? But let's just zoom in on the most important bit and translate it. This is the money shot right here. Finite sums are dense in. So in plain English, what this means is that by adding up enough of our little dimmer switch functions, you can get as close as you want to any continuous function. The network's guess can be as accurate as you need it to be as long as you have enough of those switches. It's a guarantee of possibility. Now, that sounds absolutely incredible. It sounds like we've found the key to building anything. But this is where the paper gets so interesting and frankly why it's so often misunderstood. There is a huge catch. So, the theorem promises that a network capable of solving your problem exists. It's out there somewhere. But it tells you absolutely nothing about how to actually find it. It doesn't say how many dimmer switches you'll need, what their settings should be, or if you could even build the thing with today's computers. Let's go back to our recipe analogy. It's like a cookbook telling you that a recipe for the most perfect cake in the world is possible, but it doesn't tell you that you'll need a kitchen the size of a city, 1 billion pounds of flour, or that it might take you 1,000 years to bake. It just says, hey, that perfect cake, it's theoretically possible. And you know what's wild about this? This isn't some new criticism that people came up with decades later. The author, George Seibenko, he knew this all along.
He put the warning label right there in the paper itself, in the conclusion.
He literally wrote this in his conclusion. He suspected that for most real-world problems, the number of dimmer switches you'd need would be astronomical. Astronomical. He knew he was proving something was theoretically possible, not that it was practical. The magic trick works, in theory, but you might need a stage the size of the solar system to pull it off.
So this 1989 paper gives us this incredible guarantee that a solution exists, but at the same time it warns us that finding it might be practically impossible. And that leaves us with the real billion-dollar question, doesn't it? If the original theory required an astronomical number of parts, what's the secret that makes modern AI actually work?